So in this section, you're going to learn about Taylor series and Maclaurin series. And we're going to look at how we know if they converge or not, and how to express functions as a Taylor series or Maclaurin series. So in this section, we're going to focus mostly on Maclaurin series. But to define both series, so a Taylor series is a power series that's centered at C. And then what happens with your Taylor series is, so we have this power series, and if we get each term multiplied out, this is what we get for our sum. And we know its interval of convergence is whatever the radius is. So C, if that's the center, would be C minus the radius would be the lower end of the interval, and then C plus the radius would be the upper end of the interval. Then we can define that series to be this function f of x. So we have this function f of x that we're saying is equal to that particular power series. If we take the derivative of that series, we use the power rule for taking the derivative of that series. And then if we take the derivative of each term in the series, this is what we get. We end up with, for the second term, we end up with multiplying by 2 and then subtracting that power from 1. For that term, multiplying by 3, subtracting the power from 1, and so on until you get to n. Second derivative works the same way. So we take the derivative of this one and we use the power rule. We end up with this. Third derivative, we end up with this. So we can conclude then that for any order derivative, if we do the nth order derivative, then we would keep going in this series just like we were with this pattern, where we'll have k times k minus 1 times k minus 2 all the way to k minus n plus 1. Because in this case we had the third derivative and this went to k minus 2. So each derivative then, instead of the k's, we would have n for the nth order, whatever order this is. So if it was the fourth derivative, n would be 4, fifth derivative, n would be 5, and so on. In each derivative, if x equals c, then we would plug that value in to each function. So f of c would be a sub 0. F prime of c would be a sub 1, f double prime of c would be 2, a sub 2, and so on, if we're plugging c into each of these, because every other term is going to cancel out except that first one for each function. Well, if we solve for a sub 0, a sub 1, a sub 2, a sub 3 in each of these equations, we end up with a sub 0 is f of c, a sub 1 is f prime of c, a sub 2 is the second derivative evaluated at c over 2 factorial. The third term is the third derivative evaluated at c over 3 factorial, and so on. So we can say each term in that series is going to be whatever order derivative you're on, evaluated at c over that number's factorial. So we get this equation here, that f of x could be written as this particular sum. This is called a Taylor series with this x minus c. So a Taylor series means that you can take any function and expand it into a series. So any function can be written as a sum of that function evaluated at c plus the derivative of that function evaluated at c times x minus c plus, and so on. Any function can be written as this Taylor series. A Maclaurin series just happens to be a Taylor series where c is 0. So that's why we're going to look at Maclaurin series most often, because they're the easier ones to work with when c equals 0. So here, we can find a Maclaurin series to represent e to the x by using that definition for the Maclaurin series. So what we do is we start with our function is e to the x, and when we plug in 0 for x in e to the x, we get 1. The derivative of e to the x is e to the x. So again, evaluating that derivative at 0 gives us 1. And this continues for each order derivative for e to the x. So we can say that no matter what the order is, if it's the nth order, we're going to get e to the x. And evaluating that will give us 1. So that means that if we are using the definition of the Maclaurin series, we get f to the k order of 0 over k factorial x to the k. So this series means that when I plug in 0 for k, by the way, 0 factorial and 1 factorial are both 1. So when I plug in 0 for k, then that's just the function. That's f of x, because I haven't taken any derivatives there. That's 1 on the top here. This down here, 0 factorial, is also 1. So I just get x to the 0 power. I get 1. And x is being evaluated as 0. So actually, I get 0 for that first term when k equals 0. When k equals 1, I have 1. The first derivative evaluated at 0 is 1. And then I have 1 for k factorial, so that's 1. And then x to the 1 power. So my first term is going to be x. My second term is going to be my first term is going to be 1. My second term is going to be x. My third term is going to be x squared over 2 factorial. Then x cubed over 3 factorial, and so on. So what we're doing is we're saying no matter what the order is for the derivative for e to the x, we always get 1. So we can just go ahead and plug 1 into that series there. So e to the x can be expressed as the series of x to the k over k factorial. And then we could prove that for all x, this is going to converge for all x into e to the x. So this series converges. We could check that with a ratio test. and it converges to e to the x every time. So no matter what x is, no matter what numbers I plug in for x, this will become e to the x. This will become e to that power. So again, this is a great way for me to estimate what e to a power is by using the partial sum of this series. So I can pick a number for x, and I can get the partial sum for that series to estimate e to that power. To prove, and you won't have to do this, but to prove that this does actually converge to e to the x for all x's, what we have to do is we have to show it's going to be all x's in that interval. And so what we do is we rewrite that function this way. And we have to show that the limit as n approaches infinity of r to the n, this remainder here, is 0. And then that shows us that that f of x will converge to that particular function. So this is our e to the x function. This p sub n of x just represents the polynomial, or the function, the Taylor polynomial, that represents that f of x. So in our example that we just did, f of x is e to the x. We came up with a Taylor polynomial that represented e to the x, and then we came up with the series that represented that Taylor polynomial. And if we can show that that remainder is the limit as n approaches infinity, that remainder is 0, then that shows us that e to the x is that Taylor polynomial, and then therefore is that Taylor series. And so that's what this theorem says, that if we use this formula, we get a Taylor series with a remainder. If we can show that that remainder goes to 0 as n approaches infinity, then we can show that that Taylor series actually does converge to the original function that we were looking for. So that remainder is f to the n plus 1 of u over n plus 1 factorial times x minus c to the n plus 1. And u is going to be a number between 0 and x. The second thing is we can show that a Taylor series converges if the limit as n approaches infinity of that remainder is 0. So that's a theorem that you should know, that if that when we use this formula to come up with a Taylor polynomial to represent a function, that we have that remainder, and then if we can show that that remainder goes to 0 as n approaches infinity, we can show that that function actually converges, or that series converges to that function. So in this example, that's what's happening. We're going to take that e to the x Taylor polynomial and Taylor series that we came up with and show that that converges and that our remainder does go to 0 as n approaches infinity. So we have to look at two cases, and we're going to use the squeeze theorem to do this. So in case 1, when x is greater than 0, then we get this because u has to be between 0 and x. So then if 0 is less than u is less than x, that means e to the 0 is less than e to the u is less than e to the x, and we get this because e to the 0 is 1. So using the squeeze theorem, 0 is going to be less than our remainder, which will be less than this evaluated at x. If you do the ratio test on that, you will see that this function in a series without the e converges for all x. So that tells us that this part of it right here, the limit as n approaches infinity, does go to 0 because it converges for all x. And remember, that was one of the things that could happen. If our remainder equals 0, then that means it converges for all x. And so because it converges for all x, we know that that limit has to be equal to 0. So that means that this part is 0. This is e to the x. That limit is 0. So that tells us that this ratio right here does go to 0, this one right here. And since our remainder is being squeezed between these two, this is 0. The limit as n approaches infinity of this part 0, same here. So according to the squeeze theorem, this has to go to 0 also. We can do the same thing on the other end when x is less than 0. And so this is our interval here. Works the same way. We'll use the absolute value here and say 0 is less than or equal to the absolute value of our remainder. So once again, we get that limit for that remainder as n approaches infinity is 0, and therefore we've proven that e to the x really does converge. As n gets bigger, that remainder gets closer and closer to 0, and as it goes to infinity, it is 0. There is no remainder, and therefore this Taylor polynomial is a polynomial as n goes to infinity that exactly will be e to the x. So again, that tells us we don't know how to calculate that to infinity, but we do know how to calculate partial sums, and we can estimate what e to the x is. So what you will need to be able to do for the AP is to find Maclaurin expansions, so those polynomials, and then be able to write them in series form or write them in polynomial form for Maclaurin to see ones that represent different functions. So we can do that for sine of x here. So here we start with the function sine of x. We take the first derivative. And by the way, so this is a Maclaurin expansion, so c is equal to 0. So when I do f of 0, sine of 0 is 0. But the derivative of sine is cosine x, and the derivative of cosine is 1. Then the derivative of cosine is negative sine, and that negative sign evaluated at 0 is 0. And then for the third derivative, we get negative cosine 0. That evaluated at 0 is negative 1. And then we know that repeats, right? The next derivative goes back to sine. And so we have the same repeating pattern that goes on after every 4. So we can say that sine of x can be expanded into the Maclaurin polynomial to be f of 0 plus f prime of 0 over 1 factorial plus f double prime of 0 over 2 factorial, oh, forgot my x squared plus f to the third derivative of f over 3 factorial x cubed, and so on. That keeps going like that. So when we plug in what those values are, we see that the first term, all the even terms cancel out, because in the even terms, when the n is 2, n is 0, n is 2, and n is 4, we're always going to get 0 when we evaluate that at 0. So these all are going to cancel out, and we only have the odd ones. So we have this one where it's 1 So we just get x. This one, where we evaluated the third one, that was -1. So this is actually going to be a minus. We have our x to the third over 3 factorial. And as we know, that would keep going. So now we're going to change to a plus. The fourth one would drop out. So we get this 5 factorial. The 6th one would drop out, and then the 7th one changes to a minus over 7 factorial. Then we change to a plus, and so on, and we keep going in that pattern. Well, what that means is, if we write this as a series, it's an alternating series. The first one is positive, so it's an alternating series like this. And then we have all the odd powers. So it's x to the 2k plus 1. That gives us all of the odd powers, because when we plug 0 in, the first one we get is 1. When we plug 1 in, the next one we'll get is 3, and so on. And then also the factorial are those odd numbers, the same numbers. So we get that 2k plus 1 factorial. So that series is sine of x for all values of x. So in this example, we're now going to do that for cosine x. Well, we don't have to go through all of that. Cosine x is the derivative of sine x. So we can use the differentiation property to figure out what cosine x is going to be. Since sine x, we just figured out, is that series, cosine is going to be the derivative of that. So we're going to use the power rule. Well, the nice thing is it doesn't matter what power we're taking this one to. That one's going to stay the same thing. It's going to be alternating. So we're just looking at this part. This is already to the plus 1s. And so we just take away those plus 1s. And so we get for cosine, using the power rule, keep this. That's going to stay the same. But now it's just x to the 2k over 2k factorial. And again, the reason for that is we multiplied by the power that 2k plus 1. And so when we multiplied by the power that 2k plus 1 over 2k plus 1 factorial, that just leaves us with the 2k factorial. Okay, that simplifies to a 2k factorial. So this is the series for cosine, and we were able to get that because we knew the series for sine, and we just used the differentiation property to figure out the one for cosine. We can do the same thing here for the 2x. Use the one we know for sine, and then we're going to substitute 2x for x. So here, I'm just going to go ahead and plug in the 2x where we know the x would be in the sine x series. So I have the -1 to k. Instead of x, I'm going to have 2x to the 2k plus 1 power over 2k plus 1 factorial. So that's our series for sine of 2x. So there are certain series Maclaurin series that you should know, and at the end of these notes I'll give you a table of ones you should just know, because then you can use those properties that we learned in the last section to figure out new ones. You can use the ones you know and tweak them a little using differentiation or substituting in or the integral one to get the new one. All right, this is an example where we have a multiplication, and it was a lot of writing down because you're multiplying a lot of stuff, so I just took the picture as a solution, and I'm going to go through the solution with you here. So we already know what the Maclaurin expansion is for e to the x, what that series is, and we know the one for cosine x. We just did that one. So if we write those two down, this one's e to the x. That was the expansion for e to the x, if we expand out that series. And this was the one for cosine x, if we expand out that series. So by distributing everything in this parentheses to everything in this parentheses, we get this. And remember, here we're just trying to do the first 5 terms, so that would be why they quit at x to the 5th each time. So they're distributing each of these terms to these here, going from x to the 5th to these terms here. And that's where we get that. So 1 times this, x times this, x squared over 2 factorial, this term, times this, and so on. That's what this is. Then simplifying that out, all they did was they multiplied that number in front of the parentheses, or that x value, whatever was in front of the parentheses, they multiplied it through. That's what this is right here. And also they calculated what 2 factorial is, what 4 factorial is, what 5 factorial is, and so on. So that's what these numbers are. And finally, they combined like terms, got common denominators for those fractions to combine the coefficients of all the like terms, and ended up with these for the first 5 terms. So these are the first 5 terms. So if I want to know what e to the x cosine x, if I want to evaluate that at a certain number, I can use this partial sum to estimate. I can plug in a number for x, and I can estimate what that value is. This one's asking us to find the Taylor expansion. So everything that we've done so far have been Maclaurin expansions, and so c was 0. C is no longer 0 here, and it's not just x and x squared and x to the 3rd anymore, it's x minus c, so it's going to be x minus pi over 2. So keep that in mind as we're doing this problem. So again, just like any Taylor expansion, we start with f of x and we keep taking the derivative. And we evaluate those at c. So cosine of pi over 2 is 0. Negative sine of pi over 2 is negative 1. Negative cosine of pi over 2 is 0. And sine of pi over 2 is 1. And again, we have that pattern where that keeps. So from here, we can see that anytime the derivative order is an odd number, we get f. So an odd number would be f to the 2n plus 1 of pi over 2. That represents all the odd numbers, that we're going to get negative 1 to the n plus 1 power. And then anytime we have derivatives of even orders, we get 0. So f of 2n of pi over 2, that represents all the even orders of derivatives. So what that means is, using the Taylor series definition, which is f of pi over 2, f prime of pi over 2, f prime of c, and remember it's x minus c now, and then again that's over 1 factorial, which is just 1. But then when we get to the second derivative, it's x minus pi over 2 quantity squared over 2 factorial, and so on. Well, our even numbered ones, we said, are going to drop out. That first one multiplied by 0, so that one drops out. And anytime we have multiplied by 0, that term's going to drop out. And so that leaves us with these guys. And the first one is -1. We've got that, times x minus pi over 2. And then we have x minus pi over 2 to the third, because the second one dropped out, 3 factorial. And then we have another minus, skip the fourth, x minus pi over 2 to the fifth over 5 factorial, and so on. So we're going back and forth between positive and negative. We start with the negative. So when we write that as a series, remember that's -1. It's an alternating series, but it starts with -1. So it's -1 to the k plus 1 power instead of -1 to the k. And then we have our x minus pi over 2 to the 2k plus 1 power over 2k plus 1 factorial, again, because we're representing all these odd numbers here. So that would be 2k plus 1. Odd numbers here would be the 2k plus 1. So that's going to be the series that is the Taylor expansion for cosine about x minus 2. So this is the table I was telling you about. These are the Taylor series you should know. So basically this is just something that you should memorize. So this is the one we got in section 10.8. This is not a Taylor series, this is a power series. So these are the power series you should know. This is the geometric series that represents 1 over 1 minus x. That's how we get the sum for that geometric series. This is the series that represents the natural log of 1 over 1 minus x. So that's the one we did that example of where we used the integral. This is one natural log of 1 plus x. This is inverse tangent, e to the x, sine of x, and cosine of x. So these are all popular ones on the AP, where they would give you something similar and you could use what you know about these series and what the Taylor series is, or what the series is that represents that function, and adapt it to the function they're giving you on the AP.